Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and take a look at your Bellwork for the day. So this is a great warm-up for the quiz, the second part, where you'll be applying exponential equations in context. And so here, after drinking my cup of coffee, I have 150 milligrams of caffeine in my system. You can tell by the slight shakes from my hands as I walk around the room and do red marks. My body works to eliminate 22% of the caffeine each hour. Let's write an equation to model this situation. C of H is the amount of caffeine in my system. H is the number of hours since drinking the coffee. We'll answer questions like how many milligrams of caffeine are in my system after 2.75 hours. And then lastly, how long will it until I only have 10 milligrams of caffeine? And so let's go ahead and take a look at the first one. C of H is going to be the title of my model for the amount of caffeine in my body in milligrams after 8 hours. And we know that 22% of the caffeine is eliminated each hour. And so if 22% is eliminated, what's the percent remaining? Well, I can figure out my percent remaining, that is my base B value, by taking the difference between 100% and 22%. And so what's the percent remaining then going to be for our base B? Olivia, H? 78. That's exactly right. And so if 78% remains after each hour, that's telling me that my base B is going to be 0.78. That is 78% as a decimal. So let's go ahead and start out with my general model. My general exponential model is y equals a times b to the x, where b is my percent remaining, right? A is my initial value, and then we see our variables up in the exponent for an exponential equation. All right, let's go ahead and rename that y equation C of H. So C of H will be given by A, my initial value. My initial value was 150 milligrams. My percent remaining is 78, so my base B is 0.78. And then to the x, my variable's up in the exponent. Oh, sorry, it's not going to be x, is it? It's going to be H for the number of hours since I drank my coffee. So we'll use H for our independent variable. Awesome. So the 0.78 is the trickiest part, but once we have that percent remaining, now we're ready to do things like evaluate or figure out how long it'll take until I have 10 milligrams of coffee remaining. So we'll just do a straight evaluation for letter B. How many milligrams of caffeine are in my system after 2.75 hours? We'll simply evaluate my function, 150 times 0.78 to the, and in my to the, I'm going to put 2.75. We're evaluating my function. So I could do this on my home screen, certainly, and go ahead and enter 150 times base is 0.78 to the, lag, to the 2.75. Is that right? Awesome. And so it looks like the calculator says about 75.74 milligrams. Does that seem reasonable? Well, certainly. We started out with 150, and it's now been several hours, and so it makes sense that I'm going to have less, right? I'm going to have less milligrams in my system, so that seems reasonable. So we'll go ahead and say about 75.74 milligrams. As you already got that, so who else already got that? So if you got the 0.78, then you're good to go. Great. Let's go ahead and then answer the trickier question. How long until I have 10 milligrams of caffeine left? Well, in this case, we're not going to take 10 and plug it in for H the way we did with 2.75. In this case, 10 is a Y value, a function value, of milligrams of caffeine per C. So we'll plug that 10 in for C of H, and then we'll solve. So we'll go ahead and do 10. We want to know when that equals my C of H function, 150 times 0.78 to the H. And so we'll go ahead and erase that H, because that's just about the ugliest H I've ever seen in my life. That's the second ugliest H, but we're going to use it. So here we go. Into the calculator. Let's go ahead and enter a function. Call it y sub 1. That's my blue C of H function, 150 times parentheses 0.78 to the x. There's my exponential function. A second function in red for my constant function, 10. I want to know when my caffeine function equals 10 milligrams. So I'll do two functions. I'll graph them on the same xy coordinate plane and then use my built-in capabilities of the grapher. Second, calculate intersect to see when the one curve equals the second curve. All right, so let's go ahead and get a window. I'm going to go ahead and take a screenshot of that. But for a window, I need to consider plausible values. And so we've already seen, right, that after 2.75 hours, my caffeine is down from 150 to 75, and we want to ask about 10. So I'm thinking we want to do a window like -2, just so I can get a good picture, up until, and I'm not sure, so I'm going to go maybe 15. So if I go -2 to 15 as a starting x window, that might be wrong, right? Or it might not be a good picture, but I'll try. So -2 to 15 for x's. Keep your x scale at 1. Then my y's are milligrams caffeine. So I'm going to go, I know I can't have negative, right? I know I can't have negative milligrams of caffeine in my system, but I want to get a good picture. So I'm going to go -25. And I started with 150, so I'm going to go 175 for my y max. Is that a good window? I don't know, but I'm going to try. I want to be above my 150, and I want to be below the 10 that I asked about, so I'm trying to get a nice window. So I'm going to go ahead and try this and see what it looks like. Graph. And here comes my caffeine function. And here comes my constant function. By golly, I think we have a decent window. So now, what buttons do I push to figure out when the C function equals, right? The red function, graphically, my constant function, what buttons do I push? Katie, F?
Second trace.
Absolutely. Let's everybody do the second trace. And I want the intersect, the fifth option. Thank you. So we'll go ahead and do second trace is calculate. We want the intersection. And we'll go ahead and do first curve, enter, second curve, enter, guess, enter, and voila! The calculator cursor jumps on the graph at the intersection when C of H equals 10. So it looks like after about what does that say? 10.9, about 10.9 hours. You guys getting that? Awesome. So it takes a while then for that caffeine to get out of my system. And that's why I always just seem a little bit on edge. Oh, I had 4 cups this morning. Just saying, look out. All right, what questions do you guys have on our exponential model? Then let's take a look at our financial application. Okay, so for our financial question, we're asked about investing $100 in a CD compounded continuously. Ooh, there's that key word, continuously. When we see the word continuous growth or continuous decay, then we're authorized, right, to utilize that formula A equals P times E to the RT. Euler's number, or that base E in my exponential function is Euler's number, about 2.718. And I hope you memorized the first 30 digits, right? I challenged Mr. Aker, right? His class was only doing 20. But that's not how we roll. We're going 30 digits past the decimal point. For 5 years at 2.5% interest, how much will he have after 5 years? So here we go. There's the keyword continuously. They're authorized the use of A equals P times E to the RT, and we'll go ahead and rewrite that. Our amount A, after my principal investment, $100, times E to the, and my R, interest rate, is going to be 0.025, times the term of the investment is 5 years, and we can just do a straight evaluation. So for this problem, we'll go to the home screen. Again, we don't need a graph for this one. We can just go to the home screen and evaluate 100 times E to the, remember E is second ln to the, or you can do the number E second division operation to get E and then caret. 0.025 times 5, all in the exponent, and it looks like a whopping $113. So I gained $13 in 5 years. Isn't that the story of my life? So here we go. Dollars, $113.31. And let's raise your hand if you already had that, please. Who already had that? Way to go, you guys. Awesome. What questions do you have about our financial application? Great, A per. That's my way of just remembering that formula. All right, so at this time, I'm going to go ahead and pause the recording as we're doing our homework check. I ask that you take out your assignment number 3 and make sure you have the proper heading. Today, thank you. So today we're going to be looking at logarithmic scales, as you know from your reading question. And 3 of them that we're going to concentrate on are on the decibel scale. What does the decibel scale refer to? What does the decibel scale measure, right? What does the decibel scale measure? Adam? Yeah, it measures relative sound intensity, right? How loud something is. What is the Richter scale, right? What does the Richter scale measure? Luke? Earthquakes, right? The magnitude of earthquakes. How big is the earthquake? And then lastly, the pH scale, right, measures the relative acidity or basicity of a solution. With water being, distilled water, neutral being 7, and then lower numbers beneath 7 are more acidic, like vinegar or orange juice, right, more acidic, and then higher numbers than 7, like 8, 9, 10, those are basic solutions. Things like soapy water or ammonia, those kinds of things that are basic. All right, so let's go ahead and get going. So let's suppose that our decibel scale, right, here is shown in the chart, where our relative intensity, right, that's what our decibel scale measures, in decibels is compared with our sound intensity, and that's measured in watts per square meter. And watts is actually a power measurement per square meter, and so when you hear that funky brake beats in the car going down the street, you hear those beats, boom, boom, boom. That's actually power per square meter, and that's why you can actually sometimes feel that, right? You can actually feel that that sound intensity. All right, so let's go ahead and use this formula to verify the decibel level of a hairdryer. Everybody go ahead and find hairdryer over in your chart. So we'll go ahead and find hairdryer is right here. And we're going to go ahead and take the hairdryer, and we're going to take our sound intensity N, plug it into our formula, and verify that it produces the correct decibel rating, which we're saying should be what? Does that look like 70 decibels for a hairdryer? 70 decibels? Okay. So what are we going to plug in for N? Well, N is my sound intensity. So my sound intensity over here for a hairdryer is 10 to the negative 5th watts per square meter. So let's go ahead and evaluate. D equals 10 times log of, and then for N, my sound intensity, we're going to go ahead and put 10 to the negative 5th. We now have an opportunity to apply some of our exponent rules, right? Properties of exponents. As we go ahead and evaluate this, it looks like we'll be able to take a quotient of powers, can be rewritten as a single power by doing top exponent minus bottom exponent. So this is going to be log of 10 to the negative 5 minus negative 12 is negative 5 plus 12, and that's 7. So it looks like we have 10 times log of 10 to the 7th. Recall from last class that a log is simply an exponent question. Log of 10 to the 7th is saying, what must the invisible base on this common log, 10, be raised to equal 10 to the 7th? What? This is saying 10 to the what exponent is 10 to the 7th? Well, 10 to the 7th power is 10 to the 7th, which means that log of 10 to the 7th is just 7, and then finish it up. That would mean that 10 times 7, by golly, is 7. So did it work out? Yes, there's our 70, and the unit on that then is decibels. Let's go ahead and take a look at another application, that is the earthquake magnitude. So the Richter scale measures the relative intensity of earthquakes so that we know if we're dealing with something that might be felt but rarely causes damage, right, to something that causes cracks in chimneys or foundations, to something where houses collapse. And so the nice thing about logarithms is that they take widely varying values, very huge quantities, right, like the relative magnitude of earthquakes, right? It takes huge quantities, like the force that is exerted when these two, these plates grind together and cause all this damage, and puts them on a nice convenient scale, right? Here we've got a nice 1 to 8 scale where we can measure things. It can kind of condenses the wide variance of those varying values into a nice convenient scale. All right, so let's go ahead and use our Richter magnitude. Then let's compare a quake with Richter scale of 5.6 and one with a measure of 6.6. And so 5, we're talking about things strong enough to wake up sleepers. And then 6 all the way to walls are cracking and chimneys are falling. So we see only one difference on the scale, but let's see the sound intensity. So how do we do that? Well, the Richter scale is based on powers of 10. So we can take the difference on the Richter scale and then do 10 to that difference. That is to say, we'll take the higher earthquake magnitude minus the lower earthquake magnitude. And that looks like 1, and then we'll go ahead and do 10 to that difference, and that will give us our times, the times more intense of the larger quake. And so 10 to the first looks like 10 times as intense. Consider the difference between a 6.7 earthquake and a 4.7 earthquake. Recall on our scale, a 4.7 is like vibrations from heavy traffic. So you can feel that if you're walking underneath an underpass, right? You can feel the vibrations from traffic. Well, that's a lot different than 6.7. 6.7 is where the walls are cracking and chimneys are falling down. So that's a big difference. But it's only 2 apart. Does that mean it's only 2 times as intense? No, it's a lot more intense. We can take the times intense by doing the larger quake minus the smaller quake, and then doing the 10 to the exponent. And so this would be 6.7 minus 4.7 is 2, right? 2 numbers on the Richter magnitude scale. But now we're going to go 10 to that exponent. And so that means it's 10 to the second times as intense. That is 100 times as intense. All right, go ahead and do the last one then. So compare a quake on the Richter scale with magnitude 3.4 and one that measures 7.8. So 3.4 is right there in maybe felt but rarely causes damage, as opposed to 7.8 is colossal. 7.8 ground cracks, right? Fissures open up in the earth, houses fall down. And so that's huge. Be ready to share with the class when I call on you. Alright, so we do big quake minus little quake, get the difference, and then 10 to that difference. So this looks like 4.4. Carson, do you get 4.4 here? So does that mean that the larger quake is 4.4 times intense? No. How do we get the times intense? Braden?
You take that and you put it to the with base 10.
Absolutely. It's 10 to the 4.4 times intense. And what did you get for a decimal on that? Did you get a decimal on that, Jackson?
Yeah, 25,118.86.
Wow, that's 25,000 times as intense, right? And so we've got a huge difference in the amount of energy released from that 7.8 quake versus the 3.4 quake. Awesome job. What questions do you have about our Richter scale? Okay, then there are a couple questions with the pH scale, but we're going to go ahead and do our closure now so that you guys have plenty of time for your quiz second half. So let's go ahead and take a look at your closure. Because Richter scales are based on powers of 10, a change of 4 on the scale is really a change of how many times more intense. Don't say it out loud, just circle it and be ready to share. Refrigerators run at about 50 decibels. and a jackhammer runs at 130 decibels. How much more intense is the sounds from a jackhammer? For that, we can just use our chart and look at the powers of 10. So we don't have to do any calculations or formulas for number 2, but we do have to count levels and powers of 10. Okay, go ahead and share the times and tenths for number 1, the Richter scale. If the change of 4 on the scale, right, changing the 4 on the scale corresponds to how many times more intense is the larger quake. Go ahead and share with the class when I call on you. Logan?
10 to the 4th.
10 to the 4th, absolutely. So go ahead and raise your hand if you have 10 to the 4th, the first option circle. 10 to the 4th is exactly correct. How many times intense is the jackhammer versus the refrigerator? Everybody, let's find it. So we've got refrigerator down here. Refrigerator down here has a sound intensity of 10 to the negative 7th watts per meter, so that's less than a hairdryer. And then a jackhammer is up here at 10 to the 1st watts per square meter. So we need to count the powers of 10. So for this, we don't need to do a formula or a calculation. Instead, we can say 10 to the negative 7th to 10 to the 1st is a grand total of what, 8 levels of 10? Negative 7 to 1 is 8 powers of 10, so 10 to the 8th times as intense. Awesome. What questions do you guys have about our logarithmic scales in context today? Then I'm going to go ahead and show you again, Unit 4 quiz is what we'll be doing in just a minute. And when you're done, you quietly work on assignment number 4. I'm going to pause and save the recording.